Hello guys! Hello everybody! Welcome back to my YT channel. As I promised, I have to vlog or to stream live regarding it's gonna be the last topic of chemical reaction kinetics. It's gonna be the transition state theory. Okay? So how can we do this? So we need to understand that this transition state is the highest amount of energy needed within the chemical reactions, in which within this range in between the chemical reactions, it consists of unstable reaction intermediates. Okay, it gonna be the reactants bond that shall partially be broken, okay, or it could be the products that can be partially produced or formed somewhere in between the chemical reactions. Even though we have a reaction that is a straightforward reaction, meaning to say uh, one step chemical reaction. For example, A plus B is equals to AB. Before going to AB in the products, there's a lot of chemical reactions involved in between. Okay, and the highest sufficient energy that these reactants could attain and achieve is called a transition state region. Okay, so meaning to say that is the point that it has an activated complex state or an absolute rate state. There's three terms for that. Remember, it's still the same with activated complex state and absolute theory state. You can replace also the state with region. Okay, it depends on terminologies, especially in future examination. Okay, if you found this type of theory question, something like this. Okay, now I have to illustrate further a graph because to understand further transition state theory, we need to have graphical representation so that we can easily understand what's going on in between the chemical reactions. Okay, we need to graph, and it's gonna be the energy diagram. Of course, when it's an energy diagram, energy will be present in plotting the y and x axis. Specifically, the energy will be the y-axis, and our reaction coordinate, reaction progress, extent of reaction, rate of chemical reaction, or the rate law will be in the x-axis. A lot, okay, synonymous with each other. It depends on the sources of the books you studied, okay, or you read, or you research. Some books putting reaction coordinate, some sources putting reaction progress, some sources putting also extent of the reaction, but these are all equal to the reaction rate or the chemical reaction rate or the simply R or the rate law against the energy. And our energy here in the transition states theory, graphical representation, we need to be specific because actually we have the general energy on these. We have the internal energy, potential energy, kinetic energy, gives free energy, enthalpy in fact is also an energy. And the heat also is an energy. So we need to be specific here in transition state theory discussion. Okay, it's gonna be our last topic for chemical reaction kinetics, and then after this we will be able to summarize all the formulas and equations and then straightforward recap of theories and principles that I discussed to all of you guys in this entire session of July to August, vlogs and live streams. Okay, now are you ready? Okay, we need to get an extra blank sheet of paper for the purpose of graphing or graphical representation. Okay, like that. Okay, my gosh. Wait for a while. Okay, gosh. Okay, now. Energy diagram. Energy diagram, it should have an energy on the plotting. It should be most of the times on the y-axis. Okay, but sometimes the x-axis could be the temperature or it could be time. It depends on the situation that you're going to graph. But in this transition state theory, specific the gives free energy in the y-axis and the rate of reaction in the x-axis. Let's agree we will just use the rate reaction, chemical reaction rate or rate of reaction to make that more common, familiar. Okay? Never mind the other terms. As long as we know already there are four terms to be used interchangeably with this x-axis. Okay, like that. So we have to plot now. Actually, we don't have to plot one by one because it's already have the theory for this established by Henry Eyring in 1935 with the collaboration of Pogliani. Michael Pogliani in 1935. That's why it came up with one equation for this. The relationship of chemical reaction rate with the dependency of the number of collisions frequency per unit time. Something like that. Okay. So, it'll be like this. Okay. So, I will graph now. Okay. It's gonna be the gives free energy, okay, on the y-axis, like this. Okay, and then we have the, I shall put Rxn or reaction rate, is this okay for you? Or shall we say rate talaga siya or whatever? So I just put Rxn to make it simplified, means reaction rate, okay? This one. Okay, very clear. Now, as usual, we need to have an example that favored on the product side. What do you mean by this, Sir Sotero? An example that favored on the product side. Product side. Meaning to say, a positive rate constant value is greater than 1, okay, and a negative enthalpy change. And negative gives free energy so that we can consider the spontaneity or spontaneous, which is negative. So, definitely exothermic reaction. Okay, we don't consider the reverse, huh? We consider first the exothermic reaction, in which this is the most usual occasion for most of the chemicals, okay, or most of the chemical reactions, okay, like that, because reversible chemical reaction. Okay, only if you are, only if you are going to have an endothermic environment or reaction. Most of the times, exothermic reaction. Okay, that's why we need to consider first the chemical reaction that favors on the product side. Meaning, there's a release of heat to the surroundings coming from the system. Okay, heat released. Something like that. Okay, I will draw now. So this is our reactant. Here, it's gonna be like this. Oh my goodness. Like this. Like a mountain. Okay, something like this is the reactant. Okay, here. Like this. Okay, and we have the products here. Okay. We don't have to specify the products because this is a general explanation. Any types of chemical reactions, as long as it will produce products. It could be a pi-molecular chemical reaction, unimolecular chemical reaction, or thermomolecular reaction, or multiple chemical reaction. Meaning to say, a lot of reactants to produce various products. Uni, meaning one only to produce product. So A equal to B. Okay, by molecular A plus B equals to AB. You have to choose on your example, especially if you're going to derive the equation. But here, we are not still going to that. We are still a discussion of the transition state theory, what exists in between the chemical reaction. As I said earlier, it produces a lot of unstable intermediates. So what's going on there? Something like that. Okay, now it's gonna be like this, the graph. Okay, we have the reactants and the products. Put that in your mind, okay, that the reactants always at the higher level compared to the products if we try to say favored on the products. Okay, like that. So try to draw in reverse. Favored to the products meaning the reactants in the higher elevation and then the products will be in the lower elevation. But don't you worry, all the purpose of discussion, they will just start really in exothermic reaction, not the endothermic. Maybe to say products being favored. Okay, like that. Okay, now we're going to, as usual, project an imaginary horizontal line, something like that, connecting to the curve, something like that. This is really the step, imaginary line. If you can remember, right, in using the steam table, saturated steam table, at temperature base, pressure base, superheated steam table, like that. Again, imaginary, like this. Okay. Okay. But here we are not concerned for the amounts, huh? We are not concerned with the amount, how many moles, how many, what is the mass, okay? We are concerned only the reactions involved, how fast, how slow, something like that, okay? So this is gonna be like this, okay? Draw an imaginary horizontal line. And after that, you have also to project a vertical imaginary line. Okay, like this. From here to here, like this. And then it will reach the topmost point, which is called the transition state theory. So we are here to discuss more on the transition state theory. Okay, transition state. Okay. Again, what's transition state? This is also known as activated complex state and absolute rate state. So three terms, okay? But we will just focus on the most common, which is the transition state. Okay, let's assume that our energy diagram, we don't introduce a catalyst to simplify our discussion so that it will not be complicated. Because actually it's just the same if you put a catalyst or a catalyst. Okay, so that we can avoid having too much of activation energy. Right. Anyway, I discussed that already, right? I discussed that already, right? Remember that one in the in the Arrhenius theory. Then activation energy, catalyzed reaction, adding catalyst. Okay, uncatalyzed reaction without catalyst. It's just like that. English only. Uncatalyzed reaction, un meaning without adding the catalyst. Catalyzed reaction meaning adding catalyst. So it's just the same, huh? Okay, and then it is expected always theoretically and technically that the catalyzed reaction, okay, should have a minimum and lower amount of activation energy to start the chemical reaction. Okay, it's not the uncatalyzed, okay? Because as usual, the catalyst purpose is to speed the rate of chemical reaction without being consumed and used up in the entire chemical reaction. And the reverse will be the inhibitor to reduce the rate of the reaction and it is not also consumed and used up in the entire chemical reaction. Something like that. And now we have the activation energy here. We will label this as activation energy. Oh my gosh. Like this. Okay? Activation energy. EA. Oh. E, capital E, and capital A subscript. Okay, like this. Okay, activation energy. In here, before going to this point here, class, going down to produce the products here, right? Here, at this point, here, the initial starts of the chemical reaction, like this, like that, it will attain an activation energy, and then we'll go to the product. And before going down freely, or the free fall, to produce the chemical reaction here, okay, like that, we have a lot of activation energy. So we need to draw several curves also in between with this big curve. Understood? There's a lot of unstable intermediate reactions that involve reactant bonds and product bonds that could be produced partially or that could break up partially. Okay, the reactants intermediate class is to be broken. That's the purpose. We need to break it out. Why? Because we need to produce a product. We cannot produce a product if we will not break the band of this reactant. Okay? That's why we have collision theory right now. This product will be partially produced and formed. Why? Because this is in between the chemical reaction. This is not yet the final stage of the products in which is being reflected downside here. Okay? You get the point? Something like that. So I have to draw at least 3 curves for further understanding that there's a lot also of activation energy in between the chemical reactions. Okay, like that. Tank, 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 like this. Let's say 3 curves only, but in the real sense of the world, in actual experimentation in the laboratory, there's a lot of activation energy that will be produced. This is only for the purpose of discussion so that we can understand really what's happening in the chemical reaction in between. Okay, something like that. So, EA, we have also activation energy 1 here in the first curve. And then the second curve, activation energy 2. In the third curve, activation energy 3. Okay? Simple mathematics, algebra. So, capital EA is equals to activation energy 1 at intermediate reaction plus activation energy 2 at intermediate reaction plus activation energy 3 at intermediate reaction, and these are all unstable intermediate reaction with each corresponding activation energy also. Okay, ganon. So it's gonna be like that. Now, so since we cannot really imagine this, as I said, to become an engineer, you have a wild imagination. So we need to treat this as a hypothetical scenario. Hypothetical meaning this is not really what we see in actual. Of course, this is only paper. Okay, so hypothetical, right? If it is in the laboratory, then maybe we can interpret our results. But this is not laboratory. There's no trials and data to suggest, to validate our discussion. Okay, it's only hypothetical that there's gonna be an unstable intermediate reaction composed of the product and the reactants. Okay, that's gonna be partially be broken or partially be produced. Partially be broken, the reactant bonds, and partially produced are the reaction product bands also. Bands meaning B-O-N-D. Okay guys, before understanding the transition theory, you have to review your general chemistry lecture. You need to understand the Lewis dot structure, okay, the electrons, how the electrons behave in the outermost shell, the electron dot structure, and also the electronic configuration of atoms in periodic table. You have also to remember that one also. And then you have also to remember the hydrogen to hydrogen bonding, H to H bonding, and then the van der Waals bonding. The covalent bonding could either be non-polar covalent bonding or polar covalent bonding. What? Polar covalent bonding and equal sharing of electrons. Non-polar covalent bonding is equal sharing of electrons, meaning there's no lone pair after the reaction and sharing of electrons of each reactants to produce the product. It's gonna be like that because if you don't have a strong foundation in chemistry related to this, it's very difficult to understand what's going on in between the chemical reaction during transition state to be achieved before producing a final product from the reactants. It doesn't matter what is the type of chemical reaction you have, that's what I discussed a while ago. Okay, ganon. Okay, now, so AA1, AA2, AA3. Okay, it's gonna be like this. Okay, so it's very clear, right? So it's gonna be like that. So I have to put here unstable intermediate reaction. Okay, like this. Unstable intermediate reaction. Okay, unstable meaning they still have the ability to collide with each other until such time they will establish the stability somewhere going to the end or the completion of the chemical reaction until it stops to produce the products. Okay, intermediate reaction. reactions. Ganon. Okay, it could be the reactant product. Reactant bonds partially broken. Guys, I want to straight this out, guys, ha? There's no chemical reaction produced if the bonds in the reactants were not broken. It should always be broken. That's why we have collision theory. To break the bonds, B-O-N-D, okay, or to break the bonding, the collision of the molecules will be bombarded with each other. So they will develop a strong kinetic energy so that they can establish the activation energy to start the chemical reaction. That's the purpose behind why we need to break the bonds in the reactants. Okay, partially broken. Okay, and then products. Okay, bonds partially produced. Okay, partially produced. Okay, so I summarize now here in my note here that it's gonna be like this. Unstable intermediate reaction composed of reactant bonds that partially be broken and products that partially produced before producing the final products. Okay, for example, A plus B is equals to the products AB. But somewhere along the way in between, a lot of chemical reactions will be happening there. We don't know. Okay? Okay, something like that. So it's very clear, right, in transition state theory. Okay? Any questions so far for this? And we need to add also the delta G and the delta H is always negative in this chemical reaction that favored on the product sides. Okay? So delta G negative and delta G negative meaning less than 0 or less than 0. Okay? And then the delta H will be negative also, then less than also 0. So this is spontaneous chemical reaction, negative delta G and negative enthalpy hit of formation or reaction, something like that. Okay? Something like this one. Okay. So if you familiarize the some common enthalpy hit of reaction or standard heat of formation, for example, for the water liquid, like this, for the water liquid is 285.9, negative 285.9 kilojoules per mole. Liquid gas, okay, 242.5 kilojoules per mole. Carbon dioxide gas, 393 kilojoules per mole. Just memorize the very common used in chemical reactions so that you will never scan the books anymore. It will take you also time. Okay? Just me in my part, I memorize only 3. Okay? The water liquid, the water gas, and the carbon dioxide gas. Something like that. Okay? And the specific heat capacity, also remember that one is very also useful. So 4,186 joules per mole Kelvin, something like that, okay? For the water and for the steam, okay, 2,010 joules per mole, like that, Kelvin, or convert that one and that's ice. 2,100, like this, the half of 4,186 joules per mole, and then Kelvin, something like that, okay? Got the point? By the way, you memorize that, right? Then if you have errors for the units, then you can convert. Okay, it's very easy to employ that in a certain equation using the PV and RP. If you doubt with your units, because if your memorization fails, then prove it. If it is really a joules in the numerator or kilojoules like this. But I think it's joules because it's a higher value, higher. Okay, thousand. So I think it's joules on the numerator. If not, if kilojoules is also 1 point something, just like that pressure, right? If it is in kilo, it will become 101.325. The same principle with pressure, right? Maybe this is really the joules because high value. Okay, like that. You understand the point? Okay, it's gonna be like that. Or it depends. We need to recompute again. But I am sure in terms of calorie per gram degree Celsius, the value really is for, for the latent heat of vaporization of water channel. 1 calorie gram degree Celsius is something like that. And 530. Okay? You understand the point? So it's gonna be like that. Okay? 530 kilojoules per mole. Okay? Something. Okay? Any questions so far? So that's it. Thank you so much for listening for this transition state discussion. I hope you understand a little bit. You can comment down below in the comment section, and then you can subscribe my YT channel if you really like this short live stream, or you can click the notification bell for some newest updates or you know, seeing your journal voice. Bye bye. God bless everybody. Okay. Thank you so much.